I would like to talk to you about a bold fMRI signal and how actually you can say something about the impact of age on the hemodynamic response function based on task fMRI signal. This is work conducted together with Guy Williams and with Rick Hanson. A short introduction. So first, if we want to investigate hemodynamic response function using bold fMRI, then the best way is to use an event-related design task. And CAMCAN data from here, from Cambridge, from CBU, is actually providing such data for 650 subjects, more or less, between 18 and 88 years old. For this CAMCAN task, activations were expected in the task, auditory, and visual cortices. There were some visual tasks. It was only to assess what is the impact of normal, healthy aging on cognitive functions, and in this case, on the hemodynamic response function. In CAMCAN study, the same experiment was also conducted with MEG, the same subjects, the same experiment. And then I'm interested in the physiology, how you can link what is going on at the neural level with what is going on actually with the bold signal. And for that, a balloon model can be used, and I will present some results for that. So first, I will show the HRFs, the estimated hemodynamic response functions plotted against age. Then I will talk about the physiology underlying the bold signal and what is the balloon model, more or less. Then I will present the results against age of the balloon model parameters, and then I will try to correlate it with MEG and some cardiovascular measures. Then I will talk about the robustness of the SPM's estimation procedure, how SPM estimates the balloon model, coefficients, and some short conclusions. So here you see auditory cortex, and the left column refers to analysis that you employ the canonical href together with the two derivatives, the temporal and dispersion derivative. Here you assume a finite impulse response href, and on the y-axis you have subjects plotted with increasing age. So what you see is on the x-axis just the time dimension, and these are heat maps showing actually how the HRFs look like. So when you have red and white values, so these are the peaks of the HRF, and when you have the purple or dark blue values, these will be the lowest values. You see there is such a link that actually when people age, the response is delayed. It's very pronounced for the canonical HRF with the derivatives, but you also see it to some extent with this finite impulse response. Maybe the peak is more or less all the time around 4 seconds, 4.5, but then you see that the main response actually shifts a bit. These are results for A1, and you see that there is this link between aging and HRF shape, in particular with regard to the location of the peak. Here you see some results for the visual cortex. And again, you see this relationship that for older subjects, the peak and the response move a bit backwards. It's not a very big difference. It might be half a second, in some cases maybe one, up to one. And in case of finite impulse response, it's primarily the main response. Here the estimates are much more noisy. So here I just plotted for every subject and for every volume of interest. Altogether there were 8 volumes of interest. The peak location of the href, again, for the canonical href, together with the derivatives, and for the finite impulse response. So there are a lot of dots because these are the numbers of subjects multiplied by the number of volumes of interest, and you see that for the young subjects, the peak is around 4 seconds, and then it goes below 5. So the relationship does exist. It's not extremely strong, but it's interesting. It exists across all the volumes of interest. There are 8 volumes of interest because everything was left-right. There were 2 volumes of interest for A1, 2 for V1, and 4 for M1. It's kind of interesting also that on this plot you see that for the very majority of the subjects and for the volumes of interest, the estimated peak location is actually below 5 seconds. And in task fMRI studies, when you apply a hemodynamic response function models, then you usually apply the canonical model, which assumes it's 5 seconds. So here, across 3 different regions of the brain and across some of the subjects, you actually have values mostly below 5. So now something about the physiology. It's really difficult to actually say what is going on between the neurons and between the bold response. So we get this and we try to, usually in task fMRI studies, what was actually changing at a neuronal level with the excitatory inhibitory balance. So what is going on is simply that the neuronal response will cause more blood to flow to the active part of the brain. Such an active part of the brain can be considered as expandable venous compartment, and that's why this model is called balloon model. So you will just have more blood suddenly in one compartment, so you will just blow this balloon, and many things will actually happen at the same time in this compartment. So it's not only blood flowing to this part that needs more oxygen, but also there will be changes in the blood volume, in the blood outflow, and the deoxyhemoglobin changes. This is all interacting with each other in a very confusing way. It's extremely difficult to actually think about what is going on like at every single compartment, because you have so many of them, you average the signal. And the balloon model is only an approximation of what is going on. Actually, the SPM doesn't even model the whole dynamics in exactly the same way as it's presented here. At the end, you get the bold response. So what you try to do with the balloon model is simply to account for those dependencies between those factors in such a way that more or less you know whether the changes are because of neurovasculature or because of neurons. And the balloon model applies a nonlinear model and differential equations, because simply those changes will be functions of time. So here I present like a figure comparing young subjects and old subjects, and what is actually the challenge of combining within one study people with different ages. So what happens when people age is simply that there will be changes in cerebrovascular reactivity, and this will lead to differences in vasodilation. More explicitly, like for old adults, it will be more difficult for the blood vessels to expand. This will mean that for old subjects, the cerebral blood flow will not be as strongly increased as for young subjects, and the same will happen for cerebral blood volume, and at the end, the bold signal will not be as high for old subjects and as for young subjects, even if the neural activity is the same. So it's kind of a big challenge actually modeling HRF in such a way that you are not confounded by the neurovasculature. These are the first results showing the balloon model values. As I mentioned, I was investigating 8 volumes of interest. Here I present 4 of them. The first 2 columns refer to A1. Those 2 columns refer to V1. And the balloon model, as it is implemented in SPM, has 7 parameters. Here I present the first 3 parameters. Each parameter is simply one row, so this is something that is called signal decay. This will be autoregulation, transit time. It's difficult to interpret them. Transit time, for example, refers to the time it takes for a blood cell to travel through this compartment. And it's assumed a priori that this should be around 1 second in SPM. This autoregulation parameter will refer to the way the oscillator is actually regulated. So the different differential equations will refer at the end to some oscillator, and this one parameter actually modulates the behavior of this oscillator. On the x-axis, you will see age of all the subjects sorted sorted by age, and the dashed black line is the prior expected value taken from SPM. So what the SPM estimation procedure actually thinks what is most likely a priori, and the red lines will be just linear regression fits. So what you see is that for all those 3 parameters, for all those 4 volumes of interest, for all those subjects more or less, you see some relationship that age actually influences the parameters. So all the p-values are very close to 0. If you go to the next page, again the very same volumes of interest, A1 and V1, and these are other 4 parameters of the balloon model. The remaining 4 parameters, you again see all p-values that are extremely close to 0. These are not very strong relationships with age. Like actually this doesn't explain that much variance. We have very low p-values, but we have actually very many subjects, so it's maybe not that difficult to explain some variance with age. But this was only about the relation between balloon model and age. What age says about the underlying physiology changes. But now we can actually say something about the neural changes, maybe more, because for this study we also collected MEG. It was collected during the SCAMCAN study. And there was also already a paper published last year by Darren Price from CBU here, where the constant delay and the cumulative delay estimates from this MEG study were plotted and analyzed against age. So in that study, only auditory and visual cortex were analyzed. There was also activation in this fMRI analysis of mine before for M1. So I will combine now those previous analysis of mine with those analyses for A1 and V1. What you see here in this plot are results from Darren's paper showing that there will be a relationship against age that differs for A1 and V1. So for the auditory cortex, there will be actually constant, there will be actually no constant delay, but there will be a cumulative delay. So the first component of the evoked response will actually not be delayed by age, but then the later components will be actually delayed. And for the V1 region, it's actually the other way around. It's opposite behavior. So these are the balloon model parameters for MEG, and here I'm having again 3 parameters from the balloon model, and here these are simply the MEG measures, and you see that there are some significant values of the correlations against cumulative delay, but I only considered A1 in this plot. For other parameters from MEG, I also noticed a lot of significant relationships, but only for A1, not for V1. And for V1, I didn't notice relationship with constant delay, which one could maybe actually expect a priori given the study of Darren from last year. These results actually indicate there are relationships, but they are not very strong. I also considered cardiovascular measures, but here the problem is that there weren't actually many relationships that were kind of significant. I was a bit surprised because surely there should be some links. And what I did later was I actually investigated the robustness of the balloon model estimation. So there is some code like this in SPM, like it's pretty well hidden, like people don't really think about it when they use dynamic causal modeling that makes use of it, or if they use even balloon model. But here there are some values that are simply taken from some very old papers. Some of those old studies were actually referring to rats and some other rodents, not really to humans. And actually, I was playing with those values, changing the prior expected values, changing the prior covariances, and checking how those changes affect the posterior estimates of my analysis. Also, there was 3 years ago a paper about how to improve dynamic causal modeling, and within this study, it was actually also discussed how the balloon model is implemented and how it could be improved. And it was actually argued that the mean transit time, one of the parameters of the balloon model, should be 2 instead of 1. That the oxygen extraction should be 0.4 instead of 0.34. There is quite a lot of ambiguity actually in terms of what those priors actually are. Like most people would anyway think that these are only priors, they will not have anyway such a big influence on the estimates. So here what I'm showing is, and this is the very last time I'm showing scatter plots, what happens if I multiply the transit time with 2 almost. So again, the blue dots will be the estimates, the dashed line will be the prior, and the red line will be the regression fit. What you see is that when the transit time goes to 2, you actually see pretty much the new estimates, the posterior is just being around 2. Like even if you multiply all the prior expected values with 2, all of them, then in all cases you will just get the posteriors that are pretty much priors. This is a transformation 1-to-1. The estimation procedure in SPM is just very dependent on the priors, and it hasn't been actually ever investigated. And then I thought actually maybe these are just the prior expected values that could be a bit fixed, but also maybe the prior precision, because like if you allow the prior precision to be smaller, then actually like bigger deviations from the priors are allowed. So then I lowered the prior precision very much, actually 10 times. And what happened is that, for example, for the transit time, the posteriors were very much above what SPM uses as prior. So this data actually suggests that, for example, transit time prior is way too low in SPM. But this is 3 Tesla, like some studies in the past were using 1.5 Tesla. This can be very much dependent actually on the type of data you are actually working with. This was a bit surprising that the estimation is extremely dependent on the prior expected values, and probably the prior precision has to be lowered. So some conclusions. We observed a link between age and href response delay. It was actually significant in all the volumes of interest, but these were not very strong relationships, so I was a bit disappointed, let's say. The balloon parameter is correlated with age and with MEG cumulative delay, but only for A1. Then the 7 balloon parameters were investigated, but when I correlated those values with the cardiovascular measures, and it was only signal decay, one of the parameters is correlated, and only for A1 again. The above correlations were not very strong, and actually the reason why they were not that strong might be because the procedure, the estimation procedure, is not that robust. So when I was playing with multiplying the prior expected values and actually getting simply the priors at the end of the estimation procedure, this can simply mean that the estimation procedure was confounding the analysis. And maybe I just didn't see strong relationships because my posteriors did not really refer to the physiology appropriately. And also what is quite promising is that when I was multiplying with all the prior expected values, and I didn't see any significant relationships with age. So actually there is certainly some link between whether the priors are good or not, and whether you actually see some relationship with age or with MEG or with cardiovascular measures or not. And these are the people I thank a lot for support and institutions. And if you have any questions, I'm very happy to answer.